Okay, so what we will be doing today, we will not actually get to the dry lab because we're not even close to getting through all the reactions. I'm not even certain if I'll be there. I hope to be there by next Monday where we can do that part of the time. But we have got several reactions still to go because it does deal with reactions of carboxylic acids, amines, and there is still quite a chunk of that type of information we have to go through before we can get to that. So I may wind up putting that particular lab off, and instead of it being due next Monday, it may wind up due later on. It'll just depend upon where we get to by Thursday, probably. As far as what you have going on this week, you've got an exam and you'll have one homework out of 2 that we normally do during the week. It'll only be one for that Thursday's information. But we will get the exam. I have not finished writing. Basically, I've compiled it, but it's way too long. So I've got to go in and now figure out which questions to get rid of. So I can't tell you how long it is because it's too long right now. But I will make it doable in the hour and 15 minutes that you have. Usually my goal is to make it doable within an hour. And that way everybody has that extra 15 minutes if they need it. But it's usually able to be completed within the hour is how I try to make an exam. Um, and as you've noticed on the group me, thank you for sending in notes. I have been replying as I can. I think the only one that there is that the naming questions that Zach has posted, and I believe others have posted, those did have errors on the answer key. I tried to review and see which way is correct. And there is an error on the answer key. And thus far, as the student, you have been correct in naming the compounds. The only one that there was a question about that was the primary, secondary, and tertiary carbons when you're dealing with something of this nature. And this is considered to be a 4-degree carbon. And the reason for that is because it is related to the fact that there is a double bond. So there's one carbon here, and essentially they're looking at that as a double bond. So they're looking at it as 2 carbon. So that's why that is considered to be a quaternary, is because of the double bond, which we really didn't go over when I was talking about primary, secondary, quaternary. And I mainly focused on the number of carbons, but they consider it essentially attached to 2 carbons, even though it's 1, because it's a double bond. Does that clarify?
Is that just with like benzene ring?
That's just with double bonds.
Because there was another one where
So it should be anytime there's a double bond involved that should happen, could happen.
it's like this one was, there's the double bond
This
there.
one, but this one's only attached to 1, 2 oxygens.
So if it's
So
two,
how many, it has how many hydrogen atoms are present. There's only going to be
oh,
one hydrogen
okay,
because of what it was attached to.
gotcha.
But I have been trying to keep up, what I'm trying to say is I have been trying to keep up with the group me, and even though it's been, because it's the weekend, I didn't answer as fast as perhaps I could have. If you post any questions today, I'll try to answer until about 9 p.m. At 9 p.m. I'll give up. But if you wind up having any additional questions, you can do what's been being done and post pictures, and usually I can try to answer through the pictures. Is that helping at all? The group me, some bouncing questions? Okay. Because I really do want it to be a useful tool to you and not just a waste of your time. I'm wanting it to be useful. Yes. Let's see. Okay, acetylene and ethylene are common names. So you just have to pretty much memorize those. And we went over a couple of them that were just pure common names. They're double bonds and triple bonds. Back in.
So one of these have a triple bond, why is it E-N-E-N?
Again, it's because it's a common name. It's not, it has nothing to do with its IUPAC name. So she's talking about ethylene and acetylene. I mean, not ethylene. Yeah, ethylene and acetylene. Acetylene has a triple bond, but it's not, but it's because that's its common name. It's been known by acetylene forever. And so they're not using the IUPAC naming. IUPAC naming, it would have had to end in Y-N-E. But that's IUPAC naming. If it's common naming, it would be the acetylene. Does that answer that question? So there are some you just had to memorize, like acetylene, benzaldehyde. We went over some the other day. Formaldehyde, ethylene, Glycerin, which was back with all the alcohols. Stuff like that. There's just go through and look for, well, actually, I can do it real quick. So, for example, let's see. Page 481, table 15.2 has the aldehydes and ketones that you just have to memorize. Now I'll go back into the rest of the chapters.
Alkenes and alkenes, alkenes,
These are the aldehydes
aldehydes.
and ketones that you have to memorize. Page 407. Has the acetylene. Page 428. Table 13.2 has the benzene compounds or aromatic compounds. Bless you. Oh. Page 448, table 14.1 has the alcohols that have common names. And that brings us to the aldehydes and ketones, which I've already listed. So those are the ones that have some common names that, most of them we have actually talked about. There's a couple in the alcohols we haven't, that, when you actually look at it, the benzene compounds, we went completely through those. We did go through the aldehydes and ketones. And acetylene is the only double triple bond that has a name that is that you're expected to know. That makes absolutely no sense. Simply because the ENE is typically a double bond, but it's a triple bond in that case. Does that help? Does that answer your question that you had? Yes.
Can we go over 17C? I asked you that, but it didn't really make sense to me.
Okay, so when back in the first chapter, the one that I did give you was this series. For an alkane. Okay. So basically, what we know from that particular problem is that it's an alkane. And we know we have a halogen. So it's going to do something of this nature, where it replaces a hydrogen for a bromine. Now, the only difference is that particular problem so again, we have an alkane and we have bromination or halogenation. The only difference is basically this bromine can replace a hydrogen, is going to replace a hydrogen. So one of its possibilities is to replace an end hydrogen, just like we were doing over here. But because you can replace, all you got to do is replace a hydrogen, this actually has another possibility too. In that it could replace a hydrogen off of the secondary. Now, those are its only two options because I didn't say excess bromine. I just said one bromine. So these are the only two options because if I'd have put the bromine over here, it would have been, if I put the bromine here, I'd have the same compound as I do there. And if I put the bromine there, I'd have the same compound as I do here. And then technically you also make an HBr. This is basically what it does is it forms a mixture of these two compounds. So it's halogenation of an alkane.
It needs light, right?
Huh?
It needs light.
It needs some sort of catalyst, yes.
You have to write that right.
Yeah. needs some sort of catalyst to make this happen. It doesn't want to do it all on its own. Does that better answer your question? I don't think the test is going to be quite as hard as the problem set. I'm not saying it's going to be easy. I'm just saying I'll be looking at it and I don't think it's quite as hard as the problem set. Because you're not going to have time. But the problem set was there to help you study, not to be the test.
So, going off of that, will you explain why D has no reaction? Going right after that.
That would be halogenation of a double bond. And in order to do halogenation of a double bond, you needed a catalyst. You needed something like, I forgot what all catalyst.
H2CO4.
Yeah, I think that sounds right. Yes, or FEC. Oh, well, no, that's for that. You needed. Actually, let me have a look. Where am I again? Chlorine can go on there, but it can't go. Yes, it can go. No, it should work. I need to go back and look at the answer keys to all of this, not because I need the answer key, but because I think there's a lot of mistakes. Because I would have done the with my greater confidence now than what I had way back when. I'm gonna borrow this so I can see them while we go. Oh, I know what it is. Yeah, it doesn't work. Because it's fluorine. It has to be chlorine or bromine.
One of the halogens.
So this does nothing. There's no reaction. However, if I would have done Cl2, because it's a more reactive molecule, then your answer would be so it had to do with the fact that it was fluorine.
Okay.
Took me a minute. But yeah, fluorine is very unreactive. If you look back at everything we've done, you'll notice it's all about chlorine, bromine, and technically iodine would work, but no fluorine. Fluorine chemistry is is not as reactive. It takes a lot more to make it happen. So that's the reason. So there is no reaction because it wasn't chlorine or bromine.
Just a quick question with 15A. I thought the numbering would start
It
here.
would, you are correct on your answer.
So 4 isopropyl 2,6
Hexa,
hexadiol.
yes.
Oh, okay.
I thought I answered that, but apparently I didn't.
Is that the first one or the second? 15?
Oh, it'd be like this one.
Okay.
Let me see it and I'll draw it. So that people can.
Yeah, so you would start from.
Have it all there. So the mistake was this should have been 1, 2, 3, 4, 5, 6. So it would have been 3 isopropyl, 1, 5. Hexadiol.
Not 4 isopropyl.
No, because this would have put it at 2 and 6,
Oh, okay.
which would have been higher
Then 1 and 5.
than 1 and 5.
Oh, okay. And it makes the isopropyl lower too.
It also makes isopropyl lower. Does that make sense? So yeah, you always number so that they got the lowest number.
Right.
And in this case, it had to be 1, 5. Because that's better than 2, 6. Other questions? Or get started in today's.
So, well, very fast question.
Okay, that's an octadiene or heptadiene. 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's an octadiene. Or triene or something. I haven't looked at it closely yet. One, 2, 3, 4, 6, 7, 8. I can't draw. Okay. So let's see. That direction, I feel like it's gonna be better. Because with that direction, my muscle group. Okay. So I have gone the direction that I've gone. Because yes.
What numbers, sorry? It's a verification.
Oh, okay. I don't know. I've labeled it in the direction that I have because number one, we want to start with the double bonds. They should have the lowest number possible. I also labeled it in this direction because I want the alkyl substituents to have the lowest number possible. And if I numbered it the other direction, my alkyl substituents would get a higher number. So with this, I would have called this 2,5,7 trimethyl. One, 3, 5 cyclo octa triene. Again, the 2,5,7 methyl trimethyl, once you number it, hopefully that makes sense. The 1,3,5 is where the double bonds start, and it is cyclic, so you got a cyclo. It is 8, so octa, and then you have to say that there's 3 double bonds. Even though we numbered it, you also have to say it. Does that answer your question?
Yeah.
Okay. But if I'd have numbered it any other way, my methyl group would have, if I'd have numbered it starting here, that methyl group would have wound up on carbon 8. So I would have made it a higher set of numbers by starting the numbering here.
The key said 258,
Well,
or it is 257, but we were wondering about that one because the key
it's
said.
supposed to be 257.
Right.
Other questions? Any more mistakes on the key? Or have I covered all the mistakes now?
That's all the ones that I was wondering about.
It's
1D. They said it was 1, 2 dimethyl.
This should be 1,3 dimethyl cyclobutane.
This wasn't a mistake, but I have a question about isomers. So,
Cis trans,
no, not cis-trans, just, regular isomers. So for 4, we were told to draw 6 of the 9 isomers. And I was wondering if we worked with like double bonds or triple bonds, would that technically be an isomer? of
no,
peptide?
because, well, a peptine,
Of peptine, sorry.
heptane,
Yeah.
no, because the ane means it's an alkane,
So that's.
which
the
means it has to follow the CnH2n plus 2
Okay.
formula. So if it's heptane, it has to be C7H2 times 7 plus 2, so C7H16. And if you have double bonds in there or triple bonds, you're gonna lose hydrogens.
Okay.
Other questions? It's just going to be orthomethoxyphenol because the, so let me, draw it.
Fifteen.
This one. Did I draw it correctly?
Yes.
Yes, okay. So this is one of the ones you had to memorize. That is a phenol. So since that is one part of the ones you have to memorize, that entire thing's a phenol. And so it would have to be O-methoxy phenol. Because phenol is more important than the ether. An alcohol is always more important than the ether. Now, that is going to be the easiest way to name those, is if you memorize, it's just like toluene. We automatically start with toluene as the base. That answer all the questions? Next test won't have quite as much information per test simply because we'll be back on track. But okay. So now what we're going to do is we're going to get into the new material. This is not going to be on the test tomorrow. This will be on the following test. So this starts test number, well, technically test number 2. On Thursday, I introduced aldehydes and ketones. And we talked about the naming of aldehydes and ketones. So through the naming of aldehydes and ketones is on the test. What we're going to do now is we're going to start the reactions of aldehydes and ketones. And under those reactions, we're going to talk about oxidation, which we actually have already talked about to some degree. We're going to talk about reduction of an aldehyde or ketone. And then we're going to talk about addition of alcohols to make hemiacetals. hemiacetals and acetals, as well as ketals and hemiketals. The first two are going to be straightforward, relatively speaking. The third one's going to be our challenge. Okay, so let's get into oxidation. Of aldehydes and ketones. And to do so, I want to take us back to oxidation of alcohols, because you've actually already seen all of this information and you're going to be tested on it. You just didn't know that. Didn't know that it's directly related. If you'll recall, if I have a primary alcohol, such as CH3OH, if I oxidize this with a mild oxidizing agent, this would make an aldehyde. Specifically in this case, formaldehyde. If I took and oxidized it with any other oxidizing agent, it would take this compound all the way to the carboxylic acid. If we worked with a secondary alcohol, let's go with CH3, CHOH, CH3, and we oxidize this, we get an aldehyde. I'm sorry, a ketone. If we were to try to oxidize this further, we would get no further reaction. And then if you'll recall, if we started with a tertiary alcohol, and we were to try to oxidize this, we would get no reaction to begin with. What I want to point out is this whole idea of oxidizing. You actually already know what's going to happen. Remember, this is supposed to be oxidation of aldehydes and ketones. Well, if I start with an aldehyde and I oxidize it, I get a carboxylic acid. If I start with a ketone and oxidize it, I get no additional reaction. So folks, what I'm trying to get at is you've already been exposed to the answer to oxidation of aldehydes and ketones. An aldehyde, if you oxidize it, goes to a carboxylic acid. A ketone, if you try to oxidize it, does nothing. So that's the main point here. Oxidation of an aldehyde makes a carboxylic acid. Oxidation of a ketone produces no reaction. This is the drive home message related to oxidation of aldehydes and ketones. Now, the next type of problem we're going to look at is the reduction of aldehydes and ketones. Folks, if you'll recall from, so basically, if we take an alcohol and we oxidize it, we made a C double bond O. Whether it was an aldehyde or a ketone. Well, the opposite of oxidation is reduction. So in other words, reduction is going to take an C double bond O and it is going to revert it back to an alcohol. Now, the way this is accomplished is you start out with, let's say you start out with an aldehyde and you add a reducing agent then that means that you're going to convert this to an alcohol. Now, the process is these reducing agents often are hydrides. Which are H minuses that have a lone pair. The way this works is this hydride with its lone pair if you'll recall, we talked about this bond. And we said that this bond is polar with the partial negative towards the oxygen and the partial positive on the carbon. What happens is, so this carbon is positive. Positives attract negatives. So what happens is that this lone pair is going to attack at that carbon. When it attacks at that carbon, it causes the pair of electrons in the double bond to be tossed up onto the oxygen. So what results is you wind up with this RCO minus, where this oxygen now has a full octet, and then you have hydrogens attached to your carbon. Now, if you react this in an acid, so that you have an H3O plus group floating around, the lone pair of the oxygen goes out and it snatches one of those hydrogens off. And so you wind up with your alcohol plus just plain water at that point. So, how is this likely to be written? What you're likely to see is the aldehyde in the presence of some sort of a reducing agent. And hydronium ion. That would go to make the alcohol. Or if we are talking about a ketone, again, if you have a reducing agent, an H3O plus, then you're going to get the secondary alcohol back. Folks, this reaction you are going to see again. Except we label what the reducing agent is. A common biological reducing agent is NADH. Nicotinamide adenine dinucleotide. I'm not asking you to pronounce NADH. But what happens is if we take something such as pyruvic acid, and we add NADH, originally, we're going to make an intermediate of this compound that once we add hydronium to, turns into this compound. So we went from pyruvic acid to lactic acid. And this is a common reaction that occurs in energy production. We utilize the NADH, but basically it occurs during vigorous exercise, and the pyruvic acid in our body is changed to lactic acid. And once you have a buildup of the lactic acid, that's when your muscles feel sore and achy and tired. Now, that lactic acid, that alcohol, can be returned to pyruvic acid through oxidation. So it's a cyclic process. We make lactic acid, and through oxidation, we can convert that lactic acid back to pyruvic acid. I should say, once you use that NADH, you make NAD+, which then needs to be reduced in order for it to be able to be used again in one of the cycles. But we're going to talk more about this pyruvic acid, lactic acid conversion later in the semester. Questions? If I give you an extra hour, will you study for the test? I want to go ahead and do hemiacetals and hemiketals, but I also want you to do well tomorrow. So I'm going to give you an extra hour to study for tomorrow. And then we'll do hemiacetals, hemiketals on Thursday to start lecture, which will finish up chapter 15, and we'll move on to chapter 16 about amines on. So if you are reading for Thursday, you would need to read 15.7, 16.1, 16.2, 16.3, I'll stop there. I don't know if I'll get to it, how much of 16.4 I'll go over. I've got to look and decide how important it is. Okay, go study.
Yeah.
One extra hour, or you can sit in here and study if y'all want to work together. This classroom isn't going anywhere.